Alright, so today we're continuing to factor polynomials. We start off with a little review from what we did last time. Last time we factored using the distributive law, and it went something like this. You look at a polynomial, you count how many terms you've got, and in this case we have 3 terms, and you try to figure out what do they all have in common. Usually that thing that they all have in common, those are called common factors, and what we want is the greatest amount of them, so that's called the greatest common divisor. And so the professional way here would be to prime factorize. Sometimes you can get by with just looking at them and you'll know this is 3x times x squared, this is 3x times 4, and this is 3x times 3 times x to the 4th. And writing it this way makes it obvious that you could factor out a 3x out of each of the terms, leaving you with x squared plus 4 plus 3x to the 4th. Distributive law, famous. That's what we did last time. This is called factor by distributive law. The moral of the story went like this. You look at all the terms here and you try to pick out the greatest common divisor, the GCD from all of them. That's what we want to factor out. That leads us to today. Today we take a look at the problem from a different point of view. Suppose you encounter such a problem where you try to prime factorize everything and you go, okay, let me see, what are the prime pieces here? I have a 3, I have an x and an x and an x. Here I have a 2, an x and an x. Here I have a 3, a 5 and an x, and here I have a 2 and a 5. So I've got 4 terms. And let me see, I'll pick everything, I'll get the common thing from this one, 3. This one has a 3, but that one has no 3, so 3 is not common on all of them. This one has an x, a couple x's, but this one has no x's, so x's are not common, therefore there is nothing that they all share. And so if you were going to factor by distributive law, this is as far as you can get. You really can't factor anything per se using the distributive law right off the bat. So what we need is another idea, a brilliant idea, and that's called factor by grouping. And it goes something like this. Factor by grouping. You take the exact same problem and you play the following game on it. You say, you know what, if this is given, what I could always do, I could always take that same expression and look at it, instead of looking at it as adding 4 items here, I got 4 terms at it, I can look at it as adding 2 and 2. So I could put parentheses on these 2 and put parentheses on those 2. That's legal by associative law of addition. Associative law of addition says if I'm adding 4 items, I get the same answer by adding the first 2 and the second 2 separately. So that's associative law of addition, and this is called factor by grouping, because look what happens now when you group the first 2 and you group the last 2. Out of this little group, I could factor out something. I could factor out a couple x's. I could factor out an x squared, and that would leave 3x plus 2 in here. Out of this little group, I could factor out a 5, and that would leave 3x plus 2. And that's by times table and a few other axioms, all of which can be wrapped under by inspection term. But now look what happens here. Here you see something that's common on both of them. You see this quantity here, 3x plus 2 and 3x plus 2. You could say, whoa, it looks like someone distributed a 3x plus 2. So maybe I could undistribute that 3x plus 2 out here and just see what would be left over when I undistribute that. Since this was taken out, there'd be an x squared left in there. Since this was taken out, there'd be a 5 left in there. And lo and behold, you have exactly factored a polynomial, exactly what we wanted to do, factor by grouping, not by distributive law. There's nothing that the distributive law says you can factor out of this whole thing, other than trivial things like a 1 or a -1 per se. But factor by grouping did this amazing little trick where out of the first group you could factor something, and out of the second group you could factor something, and even after that there was still something that you could factor out of both of those little groups. Famous and beautiful. This is called factor by grouping. Okay, really powerful stuff. Easy way to check your work here. Let's check our work. I could check it in green. Suppose we wanted to do a little check. A check, if you FOIL this, x squared times that would give you x squared times 3x. That's the first outer. X squared would be 2. The inner, 5 times 3x. And the last would be 5 times 2. According to our old friend FOIL. Let's verify quickly. X squared 3x, that would give us 3x cubed. X squared times 2, that would give us 2x squared. 5 times 3x, that would give us 15x. And 5 times 2 is 10. Yippee-ki-yay. That right there is nice. It's factor by grouping, and we checked our work. Okay. Let's try it again. Out of this one, you can't factor anything out of the entire, out of every one of the 4 terms. However, we're going to try our luck with the grouping idea. We're going to group the first 2 and the last 2 and see how that goes. X to the third plus 2x squared plus 2x plus 4. So I haven't done much at this point, except I'm going to associate the first 2 and the last 2. Associative law of addition says I could do that. And out of this little group, I could factor out x plus 2. I could factor out x squared. Out of this little group, a 2x and a 2, I could factor out a 2. That would leave x plus 2. Or you could do it the other way around, 2x plus 2 times 2. And now look at what happens here. This is x plus 2. And this is x plus 2. That's the common thing that they both have. So I'll put that factored over here, and so I'll have my x plus 2 set aside here, and I'll try to see what's left in there. After I factor this out, I get x squared plus 2. In other words, if you were to take this and distribute it in here, if you were to distribute it in here to the 2 items, you would get precisely the previous step. That justifies it by the distributive law. Now you've factored it. X plus 2 times x squared plus 2 is in fact the original expression. If you were to FOIL this, you could check it and see that you did it right. The first item would be x times x squared. That would give you x to the third. The outer item would be x times 2. That's that guy right there. The inside item would give you 2x squared. That's that one right there. And of course the last one would give you 2 times 2. Equivalent to 4. That's how you do it. Factor by grouping. Not everything works out this nicely, but every once in a while you could factor by grouping. There will be times when you can group the first 2 and group the second 2 and nothing good happens. That could very well be the case. But sometimes you get lucky and nice things happen when you do factor by grouping. Okay, want to try it again? Let's try that one more time. Let's try it on this one. Alright, on this one, so we're going to group these ones, and that's associative law of addition that says you could do that. You might want to just stop the tape here, stop the video, pause it, and see if you can finish that by yourself. That would be interesting, and then when you're ready, come back and hit play, and let's see how we do it. Out of these 2, I could factor out an x squared. That would leave x plus 1. And of course, out of these ones, there's nothing, but I can always get a 1 for free. X plus 1, that's because of the multiplicative identity. And here I used, of course, a bunch of other things as well. Oh, I used the multiplicative identity here. I could always get a multiply times 1 here. That leaves x squared, that leaves a 1 there, and then x squared times x, that leaves an x there. And now you can say, whoa, it looks like someone distributed an x plus 1 in both of those. So I could undistribute that and see what would be left over. If I undistribute that x plus 1, that's common on both of them, I would have an x squared there and a 1 left there. Of course, this is no more or no less than the distributive law being applied to this blue thing, that if you were to distribute it using the distributive law to both of these terms, you'd get exactly the previous line. Okay, that's called factor by grouping. Some people have trouble seeing this. Let me show you another way, just to make sure everybody gets it. If I had x squared triangle plus 1 times triangle, I could factor out the triangle and say, well, it looks like someone distributed a triangle, and that would be triangle times x squared plus 1. And that would of course be no more no less than the distributive law. That's exactly what I'm doing here, except I don't have a blue triangle. I have this expression that I underlined in blue, which is exactly the same thing. When you distribute it, you get 2 of them. Alright, hope that's clear. Anyways, maybe we try it a couple more times and see how that goes. Let's clear the screen and see how we can fare with the some of them with negatives. Yeah, we can do that one or this one with negatives. They all look good. Let's try this one. No, let's try that one. Alright, so out of this one, on this one we're going to factor by grouping again. Whoa. That was my huge head bumping into the thing. Alright, just kidding. This associative law of addition says you can associate the first two and the last two. Oh wait, you should be careful because it's not exactly addition, you got some subtraction. Always change these to subtraction, that way now it's all addition. Now it's all legal. Okay, so out of the first little group I could factor out an x squared. That would leave x plus negative 2. Again, you might want to pause the video here and see if you can finish it yourself. Out of the next little group I have x plus negative 2 times positive 1. Times positive 1. And now I see what's common. I see that the thing that's common on both of them is x plus negative 2 quantity. So I'll factor that out to the side and see what's left over. I have x plus negative 2. When that's factored out, I have x plus 1 inside. Okay? This is distributive law. And that's how you do that one. Well, that's one way to do it anyways. It's interesting to know, sometimes people ask, is that the only way to do it? What if you group the middle two and the last two? Could that work? And the question is maybe, maybe not. You should try it and see. Don't be afraid, just try anything you want. Or what if you did commutative law of addition here, switch these, and then tried it. Let's do that real quickly. What if I have x cubed plus x plus negative 2x squared plus negative 2? Commutative law of addition and some other things were used here. Out of the first little group I could factor out x squared plus 1. Out of the second little group I could factor out a negative 2. That would leave x plus 1. And now you see this will also work. I have x plus 1 and x plus 1, x squared plus 1 I mean. And that of course would leave x plus a negative 2, x squared plus 1. So there you go, done it a different way, alternative way. So sometimes different kind of groupings work and sometimes some groupings don't work. You'll just have to try it, not be afraid, and see. I think that's the best way to become comfortable with these things. Alright, talk is cheap. We should do maybe one or two more. Let's try, let me see, I wanted to try this one now. This one, yeah. So suppose this is given. I want to first turn it into addition because addition is associative and all that. 2x squared plus negative 5x plus negative 6x plus 15. That's the definition of subtraction. The advantage here is that now I'm just adding things. This is a term, a term, a term, a term, 4 terms, and they're all added. So now I can associate however I want because we have associative law of addition. We don't have associative law of subtraction. And so I'll do exactly that. I'll associate, let me try my luck with the first two and the last two. So I'll associate these ones and the last two. That's associative law of addition and see how it goes. Out of the x squared and a 2 and a negative 5 and x, the most I could probably factor out would be an x, leaving a 2x plus a negative 5. Out of these ones, probably the most you could factor out would be a, see, this is what I want, this is why I wanted to do this problem. You could either factor out a negative 3 or you could factor out a positive 3. Both of them would work, but they would just change the answer that's inside. If I factor out a positive 3, think about what would happen. That would leave a negative 2 plus a 5 in there. And then I couldn't say, whoa, it looks like someone distributed this because they don't match. This piece right here does not match that one. So that might be a good idea. So let me try a different idea. What if I factor out a negative 3? If I factor out a negative 3, that would leave a 2x here, and that would leave a negative 5. If you don't believe me, you can try it. Redo the steps here. Negative 3 times 2x gives you negative 6x. Negative and negative give you positive. This is still legal, still correct. And the second question is it helpful now? Well, look, now here I have a 2x plus 5 in blue. And here I have a 2x plus negative 5. They match perfectly. That's what I wanted because I want the next step to be something like, whoa, it looks like someone distributed a blah, whatever this is, 2x plus a negative 5. What's left in there is this, according to the distributive law. And now it's going to work beautifully. So negative 3 was the best one to factor out. Very, very important example. Shows you that sometimes you have a couple of choices. You can factor out a positive or a negative 3 or whatever, and the thing inside would look differently, and so you want it to look the same as the other one so that you can factor it out. Okay, that's factor by grouping. A few nice examples. I think that will do it for us today. We'll see you guys here next time. Take care of yourselves.